In the previous video, we left our code in a, let's say, suboptimal state. In other words, it was not compiling because the compiler was telling us that we're missing lifetime specifiers for our string slices inside of the request struct. Before we dive into the details about lifetimes in Rust, there is a little disclaimer. Lifetimes are one of the unique features in Rust. There is no other mainstream language that supports explicit lifetimes. This means that most developers have not dealt with lifetimes before, and this makes lifetimes one of the steep hills in conquering Rust, and a lot of people feel like giving up on Rust because of them. Why are lifetimes hard? Generally, we don't have to think about the lifetime of our variables, especially in garbage collected languages. When I am writing JavaScript and I create an array, like the buffer that we have in our server, for example, where is it? It's here. So in JavaScript, when I create an array like this, and then I want to store references to it, I don't have to bother with thinking about how long is this buffer going to live and are my references going to be valid, because the JavaScript runtime will not deallocate my buffer as long as I am using references that point to it. But Rust forces you to think about the lifetime of the array and of the references that point to it, and you have to make sure that the compiler has all the information it needs to be able to statically check that the references do not outlive the actual array. If after watching this video you feel like you still don't fully understand lifetimes, rest assured that this is a very normal feeling. It took me at least a week or maybe even a month before I could fully grasp the idea of the Rust lifetimes. But mastering this concept makes you a better programmer in all other languages. Alright, now let's actually explain the madness of lifetimes in Rust. In our case, the compiler tells us to specify a lifetime for the path and for the query string. It is also kind enough to actually give us the code that we can just copy paste to fix the issue, but let's write this ourselves. To use lifetimes in the struct, we have to make the request struct generic. But it won't be generic over some type, it will be generic over a lifetime. We know that we specify generics using angle brackets, and inside of the brackets we have to name the lifetime that we're going to use in the struct. Usually, lifetimes are given a single letter name, like A, for example, and to name a lifetime, we use a single quote followed by the name that we want to give it. In this case, it's A. And now we can specify lifetimes for our references using the same syntax. So we can say after the ampersand that this is a reference that has the A lifetime, and we can do the same for the reference inside of the option. But for our example, let's make the lifetime a bit more informative, because A is not really the best name. Let's think about what this lifetime represents. With this lifetime, we are saying that the request is pointing into some other memory, in our case, this buffer here. And the lifetime of the request is the lifetime of the buffer. So we can actually rename this to buff. So we know that this is the lifetime for our buffer. Now, because our request is generic, we have to give it a lifetime here in the implementation block. But we can't just say buffer here. To use a lifetime in an implementation block, or any generics for that matter, we have to declare it on the info keyword first. So we follow the info keyword with the brackets, and here we have to declare that we will have a lifetime that we can use in this implementation block, and the name of this lifetime is buff. So now we can say that our request has the buff lifetime. All right, we did add lifetimes. Let's see if our code will compile now. Of course it won't, but this is a good example of compiler-driven development. We will try until we succeed. Unfortunately, this time, the compiler gives us this very obscure message. It cannot infer an appropriate lifetime for lifetime parameter in function call due to conflicting requirements. And the error is on our from UTF-8 call. It is not immediately clear what the compiler is trying to say here, but being the best compiler in the world, the Rust compiler is nice enough to elaborate what it means. Here, it tells us that the lifetime that is trying to infer for the request and the buffer that we pass as a parameter cannot outlive the anonymous lifetime defined on the method body. And it shows us that this is the entirety of the try from function, and when we think about it, this makes sense. The compiler has some lifetime for this function body, and the lifetime of the function body would be the lifetime of all the local variables, because all of these variables will be freed once this function returns and its stack frame is deallocated. So internally, the compiler has lifetimes for every variable in our code. Let's go back to the code and try to explain exactly what is going on in this try from function. It receives one parameter, which is the buff variable, and this is just a pointer into the buffer here. So the buff is just a reference to some memory that is not owned by this function. Then we call from UTF-8 on this buffer and we get the request variable. But the request is still just a string slice, so it is another pointer into whatever the buffer was pointing to, which is the buffer here. Now we have these two different references to the buffer. Then we start passing the request to the getNextWord function, and it gives back parts of the request as string slices, but all of these variables like the method, the path, and the protocol are just more references into the buffer here. They just reference smaller chunks of it. And the compiler is actually smart enough to infer that the lifetime of the path variable should be the same as the lifetime of the parameter that we gave to the getNextWord function. Let's see how that might work. If we come down to the getNextWord function, this function takes one parameter, which is a reference, and it returns references. The compiler will implicitly give lifetimes to all of these references. But in this case, we don't have to be explicit with the lifetimes because it can figure out that there is a single lifetime for this function, which is the lifetime of the parameter that was passed. So the references that it returns will have the same lifetime as the reference that was passed as a parameter. But if we actually pass a second parameter, let's call it b, and it is also a reference, now the compiler will complain because it wants a lifetime specifier. The reason is that now it cannot infer the correct lifetime for these two references that it returns from this function. They can either be pointing to this, which is the request, or they can be pointing to whatever the b parameter is pointing to. To make this more clear, this is how this would look like internally. So the compiler will have two lifetimes here, and these two variables, will have these two different lifetimes. And now it has to try and figure out which one of these lifetimes to use. So if we explicitly say that our references are using the A lifetime, this signals to the compiler, hey, you have these two parameters, the first one has the lifetime A, and whatever I return from this function also has the lifetime A. So the compiler can make the link between the result from the function and the first parameter that had this lifetime. Also, if we put the wrong lifetime here, let's say if we make the second reference using the b lifetime, the compiler will complain because we have a lifetime mismatch. The way that the compiler can figure this out, which is also a nice way to think about lifetimes in general, is that the lifetimes are part of the type of the variable. So in this case, the request and the b variables don't just have the string slice type. The request has a type of string slice with a lifetime a, and b has a type of string slice with a lifetime b. Here the compiler can see that we expect to return a tuple with these two types. The first one is a string slice with lifetime a, and the second one is a string slice with lifetime b. But actually down here, when we are creating this tuple, we put two string slices, both with a lifetime a, because we're using the request variable for both. This way, it can figure out that there is a mismatch and we're not returning what the function signature claims we should return. But if we go back to the simple case with a single parameter, we don't have to provide explicit lifetimes because the compiler can figure out that whatever we return will have the same lifetime as the parameter that the function received, because there is no other lifetime that the return values can use. So now if we go back to the try from function, now we know that the compiler can figure out that whatever the getNextWord function returns, which is the path and the request, will have the same lifetime as the parameter that we gave to it. And the whole problem with all of these lifetimes boils down to the fact that from this function we are returning the path, which actually we can delete this to make it shorter. So we are returning the path, which is a string slice that points into the parameter here, and we're returning the query string, which points into the parameter that we received. But how this function actually looks like is here. If we replace this self with a request over the buff lifetime, so it's clearer to see what's happening, we are telling the compiler in the signature here that the function should return references with the buff lifetime, but it will actually give some random lifetime to the parameter here, like this, because we have not specified any lifetime for it. So now the problem becomes more obvious. The compiler does not know that whatever we return is actually bound to the parameter that it received, because they have two different lifetimes. And it starts to infer lifetimes for all of the variables, right? If we start from the bottom here, we see that the path is actually having the buff lifetime here, because the compiler can infer that this is the lifetime it should have. And the query string also has the buff lifetime. And then we go up. Because of this relation, it knows that the parameter to the getNextWord function has the same lifetime as the results, so it can infer that the request has the buff lifetime. And we get to the fromUTF-8 function. If we look at the function body, we see again that there are no explicit lifetimes, but the compiler will actually infer that the lifetime of whatever it returns is the same as the lifetime of its parameter. So for the compiler, this function will look something like this. The result has the same lifetime as the parameter, which is true. We are giving it the buffer, and it's pretty much just casting this to a string slice. But the string slice that it returns has to have the same lifetime as the buffer. It cannot outlive the buffer, because then it would be a dangling reference. Because the compiler knows that the parameter that we pass in this concrete case has the lifetime A, but the result has the lifetime buff because it can infer that from the rest of the function body. It complains because there is a lifetime mismatch. The invariant for the lifetime of the parameter being the same as the lifetime of the result does not hold in this case, and we get a compilation error. To fix this, we just have to explicitly state that our parameter here will have the buff lifetime, and as we said, the lifetime is part of the type, so we also have to change it up here. We have to say that the try from is for a reference with the buff lifetime, not just to some reference. And this is pretty much it. Now, what we are telling the compiler is, hey, when you call this function, you are going to pass some reference to some memory. And what I am returning has the same lifetime as the reference that you passed as a parameter. So now the compiler can make the link between the result and the parameter, and it can make sure that when we are actually calling this function and we are using the request, we cannot deallocate the buffer while still using the request. Let's go back to the console to see if our code will compile now. And yes, we have successfully compiled our code. If we go back to the editor, adding these lifetimes to the function and to the request struct does not affect the way we are calling the function and that we're using the request. If we come back to the server, we have done absolutely no changes here. We did not have to explicitly specify some lifetimes for the parameter that we're passing because there is no need for that. The lifetimes that we specify here are more like metadata that we're giving the compiler, so it has a better context about what's going on. The change now is that the compiler actually knows that whatever this function returned, which is the request here, has a relationship with the memory inside of this buffer. And for example, if we try to modify the buffer, let's say, the compiler will actually let us do that, even though the request is referencing into this buffer, and it lets us do that because it sees that we're not using the request after we modify the buffer. But if we do use the request, let's just assign it to some variable, now we get a compilation error because we cannot assign to the buffer because it is already borrowed. The compiler knows that the request internally borrows this buffer. And if we go back here and we say that the buffer actually has a different lifetime than the result, so this code will not compile again, but here the compiler will let us modify the buffer because now, as far as it is concerned, the request and the buffer have nothing to do with each other. It thinks that there is no relationship between them, and modifying the buffer will not affect the request. But we would like to actually successfully compile our code, so let's return the lifetime here, and we can delete these lines for now. We can go back and make sure for one last time that everything compiles successfully, and this is pretty much it. These are the lifetimes in Rust. Let's try to summarize all of this in 2 sentences. So, lifetimes are a very powerful tool that allows the Rust compiler to guarantee memory safety, and the lifetime parameters that we explicitly specify does not allow us to choose how long a value lives. It only allows us to communicate to the compiler that some references are related to the same memory and are expected to share the same lifetime.